Okay, so we're going to finish this section talking about that last asymptote. We know how to find horizontal asymptotes. We know how to find vertical asymptotes. So now we're going to talk about slant asymptotes. And essentially a slant asymptote, rather than approaching a vertical or a horizontal line at infinity, our function will approach just some other line, like y equals mx plus b. So now that is our asymptote at infinity, and then maybe, our function behaves something like this, okay? All right, and then this is our f of x. Okay, so let's examine this. We looked at this in pre-calculus, but of course, let's give it a calculus twist. So if we take the limit at infinity, as x goes to infinity, and we look at f of x minus the equation of that line, okay? So what do you think is going to happen to the difference between the function in pink and the asymptote if they're becoming the same? That limit should be 0 because the space is becoming 0, right? They're becoming one and the same. So if this is true, then that line y equals mx plus b is called a slant asymptote. Okay, so we're going to look at a rational function. And for rational functions, we have seen in pre-calculus that if the degree of the numerator is 1 bigger than the degree of the denominator, then we have a slant asymptote. Okay, so there's my nth degree function, nth degree polynomial in the top, and then my n minus 1 degree polynomial in the bottom. We're going to get a slant asymptote in that case. Okay, so let's look at an example. And we're going to find the slant asymptote of this rational function. Okay. So the technique we're going to use is actually something really similar to what we used in pre-calculus. We have to do long division to figure out the slant asymptote. And then we'll see, I'll show you why that works. We'll go back to the definition after we've completed it. All right, so this is exactly what we did in pre-calculus. We had the numerator and we're going to divide it out by the denominator. And we can do that because the numerator is 1 degree higher than the denominator. So we are in that case, third power or third degree divided by a second degree function. Okay, so we think, x squared times what is 4x cubed? Well, 4x will get us 4x cubed. So it's 4x, so I'm going to find the x term. So remember, all of our powers have to be aligned, decreasing order, 3, 2, 1, 0. And 4x is going to get this first term to look like 4x cubed. 4x times x squared is 4x cubed. There you go. And then 4x times negative 3x is negative 12x squared. Okay, so this is how we do our long division. Hopefully it's a review. And then we subtract. So that's going to cancel to 0. And then negative 10 plus 12 is 2x squared. And then we bring down the next term and we start over. X squared times what is 2x squared? Well, plus 2. So we have 2x squared, 2 times -3. All right, and then we come through and we change all the signs. That goes to 0. -11x plus 6 is -5x, and we bring down the 1. Okay, and at this part we're done because x squared times no polynomial will get us to -5x. So if you remember, this is called your remainder. Okay, so here's what we've discovered. If we take 4x plus 2 and we multiply it by x squared minus 3x, and we add the remainder, it gets us back to the original function, okay? And if you have a hard time seeing it, you can always look at a simple example, like 12 divided by 5. Here's our remainder. And to get back to 12, we do 2 times 5 plus 2 is 12. So 4x plus 2 times x squared minus 3x plus the remainder gets us back here. Let's write that out. So quotient times the divisor plus the remainder gets us back to that dividend. Oops, 10x squared. All right. And then what I'm going to do is I'm going to divide everything by the dividend. All right, what we divided by, x squared minus 3x, so I can get my y back. All right, that's what I'm working towards. I'm going to get my y back. So I'm going to come through and I'm going to divide by the denominator of that rational function. Okay, so we're doing this. So now this is our y. This whole thing is our y. That cancels. So what are we going to get? We're going to get our original function y. Here, bear with me, is equal to 4x plus 2. That's this part. Plus the remainder over the divisor. All right, and then y, because that whole thing is y. So now let's go back to the definition of slant asymptotes. So the limit then, as x goes to infinity, of y minus, and I'm going to subtract the quotient, minus 4x plus 2. Okay, and then we're going to summarize everything. That's going to be equal to the limit as x goes to infinity. If we subtract the 4x minus 2, what's going to be left over is this. Okay, and then as this goes to infinity, right, we can take the limit at infinity, we can divide everything by x squared. So we're going to get a 1 in the denominator, and all the other terms will go to 0. So 0 divided by 1 is 0. Okay, so we just fulfilled this requirement. The limit as the function minus mx plus b is equal to 0. Let me bring you back. The limit as x goes infinity of the function minus mx plus b is equal to 0. that means this is our slant asymptote. So y equals 4x plus 2 is the slant asymptote. All right, so the process when we're finding slant asymptotes, it's the quotient. Right here, when we do our long division, it's going to be that 4x plus 2, that's the slant asymptote.